Okay, so today we will discuss this is called Pauli theory. This is the last theory of paramagnetism that we will look at. It's called Pauli theory. So we had looked at theories of paramagnetism earlier. For example, we had Langevin theory, which is a classical theory, where a magnetic dipole can take any orientation. Okay, so then we had Coulomb theory, and here energy of dipole is quantized. And of course, we did only classical statistical mechanics. So in these two cases, if you see that the result, the final result of both these theories is that the paramagnetic susceptibility will go like C by T, where C is some Curie constant, and this is called Curie's law. Now it turns out that this result is this is good for certain materials which are called insulators. It's good for insulators. Of course, at non-zero temperatures, if very close to zero temperature, then there is a saturation that these two theories propose or give rise to. So this behavior is good for insulators. But when someone examines metals, that is when you consider metals, chi for metals, we get chi to be independent of. Okay, and this is what experiment shows you. If you look at paramagnetic, if you look at the susceptibility of metals, then it is chi to the chi will go T power 0. Okay, whereas our classical theory says that chi should be -1. So we can ask. So classical theory. This is somewhat similar to what we had in the specifically specificate of electrons in metal should go like CV, should be independent of temperature, and it should go like T to the 0 if electrons are treated obeying Maxwell-Boltzmann statistics. High temperature, of course, Maxwell-Boltzmann statistics. Whereas this CV goes like T to the power 1 if electrons obey Fermi-Dirac statistics. And that is what we have shown in previous classes. So if you are taking a Fermi-Dirac statistics, it should be like this. And we have understood this by considering the Fermi-Dirac statistics. We have shown that CV goes like T to the power. But notice that classical to quantum statistics, this is T to the 0 and T to the 1. Okay? And similarly, if you look at chi here, okay, so for paramagnetic susceptibility, we have something like this. Chi should go like T to the 1 for classical statistics, and of course chi should, experiment shows that it goes like T to the 0. Okay, so this is what as of now experiment. So since here we are able to show by using Fermi-Dirac statistics, we hope that we will be able to show this. Okay, so Pauli had shown this actually, that Pauli showed this result from FD statistics. So this is so what we have is just a free electrons, and so when you have a free electrons, so here let's assume that free electrons, so electrons in metals are free electrons. and because they are free electrons, you can say that they have orbital angular momentum to be 0, and they have spin, and this spin actually interacts with the applied magnetic field. Okay, so we can say that we can assume L is equal to 0, and the spin of electrons respond or interact with applied magnetic. Now, before we do this, let me just tell you what we used to do with respect to free particles. So this is just to recall our the way we have studied our free particles. So let's say that this is essentially I'm trying to just recall this concept of density of states. Of course, in 3 dimension for free particles. Density of states in 3 dimension for free particles. So, free particle energy is p square over 2m. And if you are thinking of a phase space, then the number of particles, so energy depends only on p. So I can define my dn as number of states of course in some sense as a number of points or you might have called this as cells such that the momentum, because momentum actually labels the state, such that the momentum is in range dp around p, the momentum like that. Okay, so is given by, so this is what my dn is, and I can write this dn to be, so I want to draw a momentum space here, because energy does not depend on the position coordinates. So I can think of a momentum space where I have a sphere of radius p and another sphere of radius. So this is p and this is dp. So this annular region will be the volume in the momentum space, or if I multiply this with v, it is the volume in the phase space. Okay, so that is given by 4 pi p square dp into v. So this is the volume in the phase space such that So this is your okay. So this has to be divided by the minimum volume so that you get the number of cells of HQ. Okay, so this is something which is very simple. This is sometimes called phase space factor. So this you can write if you want. You can write this as some G of P dP. This is given by this quantity. Now you can also write this in terms of energy, because you know P square is twice m energy, and P is square root of twice m root E. So I can get my dP as root 2m into 1 by 2 root E into dP. So I could have written this also as dN is equal to 4 pi into so I can write down twice m to the power 3 by 2 into root E, and of course there is a 2 sitting here, so that is going to give you a 2 pi here into d epsilon divided by HQ. Okay, so this is assuming that, of course, this each state is non-degenerate. But if you consider spin into account, so you have to multiply this by a spin multiplicity factor 2. Okay, so this is a spin multiplicity factor. Okay, so that is dN is equal to I have 4 pi into twice m to the power 3 by 2 root epsilon by h cube. Okay, so if you want to write this in terms of h cross is 2 pi h cross is h. So I can write that in terms of cube. So that is 8 pi cube. Okay, there is a v here which I have to keep writing v, and 8 pi cube into h cross cube. That is what this is. So that is equal to v by 2 pi square into twice m by h bar square to the power 3 by 2 into root E into d epsilon. Okay, so this is including the spin. If you do not include spin multiplicity, then it will be v by 4 pi square. That is what we have been using in Bose-Einstein statistics case. Okay, so why I wanted to show you this is the following reason. So this you could have written it as, I think if I have used this symbol A of epsilon d epsilon, and this particular factor is here A of epsilon. Now I want to just if I plot this density of states. Suppose if I plot epsilon versus A of epsilon. So this density of states will be something like this, because it goes like root epsilon. Correct? This is the graph of root epsilon. Okay. So now what is that we we have is that we know that if you take integral over this d epsilon a of epsilon. Okay, so if you just integrate this, let's say from 0 to infinity, what you get is the total number of particles, because there is only one particle in each energy level. So if you integrate the density of states, you get total number of states, and total number of states. Sorry, this is not exactly this. So if you consider this at 0 temperature, okay, so this is at T is equal to 0. Okay, I will get the total number of particles. In general, that means I don't have to talk about 0 temperature. So in general, I can write down integral 0 to infinity d epsilon a of epsilon. If you talk about finite temperature, then each of these energy has got certain probability of occupation. So if you include this probability of occupation and then integrate from 0 to infinity, then you get the total number of particles, and this is valid. This is a valid expression for any temperature greater than or equal to 0, because you know what is P of epsilon at 0, at t equal to 0, it's like that, right? So you can see that if you want to sorry, if you want to plot this density of states, suppose let's say I want to plot this integral. Okay, so let's say that I have energy, and then I have to plot A of epsilon times P of epsilon. Okay, so first let me plot it. Plot this one at. So let's say you have some Fermi energy here, epsilon. So this graph looks like this. It will be like this, and when it comes to this, it abruptly becomes 0, because you are multiplying with this P of epsilon, and P of epsilon is 1 up to that point, and then 0 after that. So this is the product of A of epsilon and P of epsilon. This is for, so this curve that I have drawn is for t equal to 0 Kelvin. Now what happens at higher temperature is something which we have discussed, and it is not very difficult to draw, because whatever happens, P of epsilon is going to get modified slightly around epsilon. That means I'm going to have more or less the same picture like this. Let me draw this almost like this. But here, there's going to be some kind of a change like this. So around P of f, there's going to be some change. Of course, this is going to go to 0 only as epsilon goes to infinity. That is why we have to integrate from 0 to infinity. But this is what your product of density of states and P of epsilon is. So what I wanted to impress upon you is that in order to find out what is the number of particles, it is necessary to think of, see, what is total number of particles? Total number of particles is area under this curve. Okay. So this is what I have plotted here is T for non-zero temperature, T greater than 0 Kelvin, and this particular area under this curve gives you n. That is the integral of this. Correct. So the shape of density of states is very important in determining the number of particles. Okay. Now what we so if you understand this, this is what we have done last time when we did the electrons in metals, because there we try to do this integral by using Sommerfeld's expansion, and there we found out. So the expression for the chemical potential in terms of the temperature is obtained only from evaluating this integral, if you can recall. Okay, so now what we will do is, so now in this case we have a different situation, because now we are interested in talking about the magnetic properties of the electrons in metals. So we are going to apply magnetic field. Now what happens if you apply magnetic field? So we have the particles. So when you apply magnetic field, so when we apply magnetic field, then the number of particles, so then number of particles actually they split into two groups. Split into two groups. What are the two groups? So the first group is so particles whose spin is parallel to the applied field. Okay, so you will call this as upspins. Upspin particles. Now, because this spin interacts with the magnetic field, the energy of energy of such particles is, in addition to the kinetic energy of so let me call this as some E up. So in addition to the kinetic energy, there is going to be an energy which I will call it as some mu b. This is the Bohr magneton. This is the magnetic moment, okay, into some applied field H. Okay, so this is the applied field. Okay, this H is applied. Okay, so this is the energy of. So there is going to be some decrease in the energy of all these particles. Earlier, without applying magnetic field, if the energy was p square by 2m, now after applying a magnetic field, the energy will decrease. Okay, that is what this shows us. The second group of particles are the ones, so particles whose spin is anti-Pauli. Whose spin is anti-parallel. Anti-parallel to H, applied. So we call them as downspin downspin particle. And because the energy of these particles will be E square by 2m plus mu b into h. Because you know the interaction of the magnetic moment with the field is minus mu minus magnetic moment dot the applied field. So parallel means theta is 0, cos theta is 1, and anti-parallel theta is 180 pi, so cos pi is minus 1. So because of that, you have an increase in the energy of the anti-parallel configuration and decrease in the energy of the parallel configuration. Now what happens is except this change, there is no other change. That means if you are looking at so now I may have to worry about the density of states for each one of this group of particles. So I may consider, except for this change, there is no difference. These are free particles anyway. Okay. So now what happens if I plot, if I look at the density of states for this this kind of a thing, whatever was the density of states for energy 0 will be now the density of states for the energy minus mu b. Remember, h is small. Okay, so in general, our h is very small. We apply a very small magnetic field. Okay, so it's a small shift in the energy, small dip in the energy, but nevertheless, the density of states will be shifted. So let me try to consider the density of states for each one of these separately. So for upspin particles, okay, so particles with spin up. Okay, suppose let me consider this particles with spin up. So if I have to plot my density of states as a function of E, and as I told you, whatever was epsilon equal to 0 will be now minus mu b. So it is the same form, but it will actually go like this. Okay, so this is essentially minus mu b into h. This point. So it doesn't start from 0, but it starts from minus mu b h. Of course, this is positive. So what I'm plotting is, in some sense, A up of E. Okay, so that is the density of states corresponding to that. Now, on the other hand, if you are trying to plot the same graph for particles with spin down, particles with spin down, that means those particles that are anti-parallel. So if I have to plot this graph, epsilon versus A of epsilon. So when whatever happens at momentum 0 will now happen at mu b. So it doesn't start from 0 here, but it starts from 0 here. So this is going to be your, so this is plus mu b h. So the density of states actually gets a little bit changed because of the applied magnetic field. If there is no magnetic field, then both of them starts from here, and there is no difference between upspins and downspins. Okay, then the total number of particles will be simply 2 times this number of particles. If you take this, it is just half of the particles. Okay. Now, it is customary to represent these two together in one graph. So, in magnetism literature, people try to draw this graph in the following fashion. So, uh, the two curves of density of states are represented as follows in a single graph, by where the energy E is along y-axis. Okay, E is along y-axis, and A of epsilon is along x-axis. It is like we are going to invert this. So if you invert this, what happens? You're going to have E in this fashion. So that is, let's say you have E. Okay, so if this is your A of epsilon, and if this is your E, this is your epsilon, then you start from here, and then okay. Now, if you are plotting this, then you're going to write A of epsilon and epsilon. So you start from here, and then this is just rotating. But to represent these two things in one graph, what one does is the following. It is a useful picture. So the way it is drawn is that you plot this energy So let's have this energy here, and you plot a up of epsilon on the left hand side and a down of epsilon on the right hand side. Okay, so it is not that this is negative, this is positive. It is just represented on both sides. So that means here you are going to start from here and then draw a picture like this. And here we are going to start from here and draw a picture like this. Okay, so this distance in the energy is 2 times mu BH, because this is plus mu BH and this is minus mu. Okay, so this is kind of a general way in which spin density of states. Okay, so this is what is called spin density of states. Is usually represented in this fashion. Now, the point is that when you are trying to suppose, let's look at zero temperature situation. So in the zero temperature situation, there is some highest energy that that these particles will occupy. So if, right now you are considering them as two independent set of particles. So that means if you are just forgetting that the other particle is there, then there will be some Fermi energy for the highest occupied level for up spin particles and some highest occupied level for the down spin particles. Okay? So whatever was the Fermi energy which was there earlier before applying the field will get shifted down for one particles and it will get shifted up for the other particles. Now, what happens is in that case, because there are some levels that are available that are empty below Fermi level, these particles which are there in the downspin will get converted into upspin. By reorienting their spin, they will occupy those levels that are free in the upspin level. So in equilibrium, there is going to be one uniform level. So this is your Fermi level. Okay, so the Fermi energy. So in equilibrium, we have a common Fermi energy for both particles. We have a common Fermi energy for both the particles. Now, this is basically what equilibrium is all about. If so, what happens if the Fermi energy is different? So, if epsilon f for down particles, downspin particles is higher than that of upspin particles, which can be the situation, the case, as soon as one applies the magnetic field. As soon as one applies magnetic field, that could be situation. So then particles lower their energies by converting their spin from down to up such that a common EF is achieved upon equilibration. Okay, so this is what when I meant to say that in equilibrium we have got a common EF. But now, as I told you earlier, that the density of states, when you actually try to um, find out the number of particles, it is essentially the area under this curve. Okay, so I think I will have n plus. Okay, so I can call this as n plus. This is n up. Maybe I should. So I should call this as n up. N up is the area under this curve. So if I have this area, if I calculate this area, then that is what gives me n up. On the other hand, if I have area under this curve, is what gives me n down. That is number of particles that are down. Okay. So that means because of this common EF, so this area under the curve will give you n down. So it is easy to see for you that n up is greater than n down. Okay, so I think it's easy to see. Okay, so note that n up is greater than n down. Okay, so this is what leads to magnetization. Okay, so and this leads to magnetization. So one can define magnetization. So we can write down magnetization to be the Bohr magneton. This is the magnetic moment associated with each one of them, into your n up minus n down. This is not spontaneous magnetization, but this is the magnetization that is a result of the applied magnetic field. So the system has got magnetized. The metal which has free electrons is getting magnetized. Okay, so this is how the magnetization is, and then you can find out the susceptibility as magnetization divided by volume into magnetic field. Of course, you have to take this in the limit. This h goes to 0. Okay, so this is your susceptibility. So we have to calculate using this density of states, this n up and n down, and then from there we can find out the susceptibility. Now this situation is quite simple, because so first let us try to look at this expression like this. When we looked at the density of states, we had seen that the density of states for free particles, the expressions like this. Now this density of states simply tell you that your momentum, the kinetic energy starts from 0 and then it goes all the way up to infinity. Okay, so I want you to just keep this in mind. So the fact here is that for a free particle, so E square by 2. Hello? Varies from 0 to EF at t equal to 0. Okay, and it is because of this p square by 2m, and I have my energy is equal to p square by 2m. Okay, so now I want to use the same expression of the density of states. But now what happens in this particular case, you can notice that for upspin particles, so note for upspin particles, p square by 2m, there is a kinetic energy, varies between between 0 and epsilon f plus mu b into h at t is equal to 0. So, to find out n, okay, please note this carefully. And the same way for downspin particles, this varies between 0 and epsilon f minus mu b h at 0. So I can get 0 Kelvin result by simply just 1 minute. Hello? Hello? Ama. இதுதானே ரேஷன் கார்டு தானே? Sorry. So downspin particles will be varying from 0 to epsilon minus mu. So what I'm trying to do is that I'm trying to say that if I replace, okay, so
Sir,
yes,
for upspin particle, that will be sigma x plus will be h or minus.
what?
For upspin particle,
Uh,
sir, how it is sigma f plus mu b h at t equal to 0 Kelvin?
yeah, so what I'm saying is that if you look at this one, this energy, okay, so this is the energy for upspin particles, right? So p square by 2m, so highest energy is epsilon f,
Yes, sir.
okay, and that is common for both. That's what we
Yes.
argued. So what is the variation of p square by 2m is it will be epsilon f plus mu b into h. whereas for down it is epsilon f minus mu b into h. That is the range of kinetic energy.
Yes, sir.
So essentially, what I'm trying to do is I want to make use of all our expressions that we have already learned it, so that I think so to get to get an expression for n up. Okay, to get an expression for n up. So I'm going to simply replace epsilon by epsilon plus mu b into h. Epsilon plus mu b into h in the expression for n is equal to integral 0 to okay, let's call this 0 to infinity d epsilon a epsilon into p of epsilon. Okay, so of course I have to say that in a of epsilon, for the expression for n is equal to this. Okay, so now what is this implies? This implies that this n up can be written as integral 0 to infinity d epsilon. Now a of epsilon plus mu b into h into p of epsilon. Okay, so as we have seen that the density of states as a change like this, and this is what you get for n up and n down. N down is equal to integral 0 to infinity d epsilon and a of epsilon minus mu b into h into p epsilon. Okay, so if we are able to get this n up and down, then we are done. I think we can get this expression. Now you can see that this n up minus n down. So my magnetization here is mu b into integral 0 to infinity d epsilon and p of epsilon. Let me put it this way, into a of epsilon plus mu b h minus a of epsilon minus mu b h. Okay, so this is the expression for the magnetization. Now, since mu bh is very small, compared to the energies that are important compared to epsilon, we can expand a of epsilon plus mu plus minus mu bh. Okay, around this epsilon. So if you do that, I get. Let me just expand it and keep the first and second terms. P epsilon, P of epsilon, and I have so A of epsilon plus mu B H into d A of epsilon by d epsilon minus A of epsilon plus mu BH into d A of epsilon by d epsilon. So the A of epsilon will cancel here. So I will have 2 times mu B square H integral 0 to infinity d epsilon P of epsilon into d A of epsilon by d epsilon. Higher order terms, of course, I have neglected. There are terms here, there are terms here, and I have neglected them because mu BH is very small, so square terms are not. Now I can once again do this trick of doing an integration by parts. So I write this 2 mu B square into H, and then I write A of epsilon into P of epsilon evaluated from 0 to infinity minus integral 0 to infinity d epsilon A of epsilon into dp of epsilon by d epsilon. Okay, so this is what I did was integration by parts. Now this is we know what is A of epsilon, but we definitely know that A of epsilon at epsilon equal to 0 is 0. And we know that P of epsilon at epsilon equal to infinity is 0. So this one is actually equal to 0. So I have something like 2 mu B square into H integral 0 to infinity d epsilon A of epsilon into, let me write this as minus dp of epsilon by d epsilon. Now one can think of writing this. I'm sure you recall that what is this minus dp by d epsilon. Okay, so first let us consider t equal to 0. Okay, if you consider t equal to 0 Kelvin, then your minus dp of epsilon by d epsilon is a Dirac delta function of epsilon minus epsilon. It's a negative dp by d epsilon, but there's a minus sign, so this is negative. So in that case, what happens? This magnetization is equal to 2 mu b square h into, if I substitute that there, then I have A at epsilon. Okay, so what is A at epsilon here? We have seen that 2 mu b square into h, and a at epsilon f is you take from this expression that we have derived. So here, so this is your a of epsilon, right? Whatever this bracketed quantity is your a of epsilon. So you are going to substitute that one there. So you have v divided by 2 pi square into twice m by h bar square to the power 3 by 2 to epsilon f power 1 by 2. Okay, so that's your magnetization. Okay, so if you are trying to look at so you want to substitute in general. Okay, so look at this. Okay, so let us write chi. Chi is m divided by v into h. Okay, so I have v here, h here. That's equal to this 2 will cancel. So I have mu b square into twice m by h bar square to the power 3 by 2. Of course, by pi square into root epsilon. Okay, but we can look at if you don't bother about up spin, down spin, etc., then you could have written this as n is equal to simply 0 to epsilon f of d epsilon into a epsilon. Correct. So that is given by v by 2 pi square into twice m by h bar square to the power 3 by 2 into epsilon f to the power 3 by 2. So you take this 1 here and n by v here and call this as number density. So you can write down this 1 by pi square into twice m by h bar square to the power 3 by 2 can be written as twice n divided by epsilon f to the power 3 by 2. So let me write that down for this expression. Yes, chi is equal to 2n mu b square divided by epsilon f. Okay, so this is an expression that is what we get at t equal to 0. Now look at this. This is independent of temperature, independent of T. That is one feature, and also varies as n. If n is your density, it varies as n, and it also varies inversely with respect to EF. Okay. Now we have seen earlier that our classical theories. Okay, so classical theories show that. Okay, so maybe I can call this as chi 0. This is a t equal 0. So at higher temperature, chi infinity, this will be of the order of n mu b square by some kb. Okay, this is of that order. Of course, there may be some constants, but then you can immediately see that the ratio of this chi0 to chi infinity is of the order of, so I'm only mentioning the order of is kBt over epsilon. And kBt for most of the operative temperatures is much smaller compared to epsilon, as we can. So this is very small. Okay, so that is your zero temperature susceptibility. It is independent of temperature for metals, and it is a small quantity compared to the temperatures that you will see at the finite temperature. So this is what we have at 0 Kelvin. Now at finite temperature, the business is same as what we have discussed earlier. So what happens for now consider T greater than 0. So in this case, what happens is that you have to go back to this expression. It is not Dirac delta function in that case, but nevertheless we know that it is kind of a sharply peaked function, and so I have to use the Sommerfeld expansion to get this. So I have to write down something like this. So you have your magnetization is equal to mu b square into, of course, I write v by 2 pi square into twice m by h bar square to the power 3 by 2. This is what we have. So I can actually rewrite this using this expression. So I have 2 pi square is like n by epsilon f to the power n. So that I can, because so what I'm trying to say is that you know that the number of particles are not going to change. So this is something like n mu b square divided by epsilon f to the power 3 by 2. And then I have an integral from 0 to infinity d epsilon and epsilon to the power 3 by. Okay, so I think I have. Yeah, so I think a of epsilon. So that is epsilon to the power half into minus dp by d epsilon. Okay, so now what I will do is I have to just now expand, use the Sommerfeld expansion. Okay, so you can use expansion. What did we do? We tried to write epsilon to the half as mu to the half plus epsilon minus mu into half and mu to the minus half. Okay, plus epsilon minus mu the whole square divided by 2 into half minus half mu to the power minus 3 by 2, and of course so on, but we will be interested only around mu. So as I think in the last, let's just look at some of the expressions that we had already derived. Instead of doing this exercise again, so let me just yeah. So I think we had epsilon to the power 3 by 2. Yeah. So I think we had expressed these integrals. So the second integral is, first integral is just 1, second integral is and the third integral is, so I had written down this I mu is so I0 mu is I0 mu is 1, that is mu power 3 by 2. I1 is 0 and I2 is I square by 12. I think I have to add that. So I think I will get exactly the same result because I have let us look at that. So I have so if you go back to this expression, I will have m that is equal to n mu b squared by epsilon f to the power 3 by 2 into integral 0 to infinity. The first one is the epsilon and mu to the power half into minus dt over d epsilon. That is the first term. Second term is half mu to the power minus half into epsilon minus mu to minus dt over d epsilon. Okay, so these are three different terms plus minus 1 by 4 mu to the power minus 3 by 2, and of course there's a 1 by 2 sitting there, epsilon minus mu the whole square into minus d. And of course there are other terms which we will neglect. So this integral will give you 0, and this integral will simply give you 1. So that means you have n mu b square by epsilon f to the power 3 by 2 into mu to the half plus I have minus 1 by 8 mu to the power minus 3 by 2 mu to the power minus 3 by 2 into this integral integral over this one. This is what that x square that gives me kt square. So I get a kt square, and the epsilon also gives me a kt. The epsilon. So I'm going to use this, right? Epsilon minus mu by kt is equal to x. So x into kt, the epsilon is also into kt. So I get kt outside. Then I have kt square here. And I think I get some pi square by 12 or something like this here. Okay, so anyway, so I want to tell you that when you are trying to look at susceptibility, okay, so we get susceptibility as chi 0 into 1 minus pi square by 12 into kbt by epsilon f square. So this is the expression that we get as a function of temperature. Okay, so this is in agreement with the experiments, and we have seen that a similar expression we found out. Of course, you have to use that expression for mu. Okay, so to get this one, use the expression for mu as a function. So if you use that expression, which we derived in the last one of the last classes, then you can show that this will be this. So you can see that probably this is not how Pauli did it, but since we used Sommerfeld expansion, I've tried to use that Sommerfeld expansion to show that this can be obtained in this fashion. So the main idea is that there is kind of shift in the density of states, and that gives rise to more upspin particles. Physically, it is not very difficult to understand because the moment you apply magnetic field, many spins will try to align along the direction of the field and the spins that are anti-parallel to the field. And that is what we are trying to put it in this language of density of states to calculate the quantities of interest. Okay, so this is what is called Pauli theory of paramagnetism. And for metals, you have this independent of temperature as a leading term here. Of course, it depends on T square later, but leading term is independent of temperature. That chi 0 is independent of temperature, and that is what is observed. Now, as I have shown here, that I mean, this is something which I was thinking when I was trying to present this. As you can see that specifically, if you don't consider these electrons to be obeying Fermi-Dirac statistics, it is 0, and if you consider them to obey, it is 1, and here it is -1 and it is 0. So I was just wondering whether there is any general thing that we can say that So when you take a color, so let's say you have. So please don't think that what I'm saying is an established knowledge. This is some kind of a thought which I'm just trying to present, but it may be right and it may not be right. So the thought is that the moment you consider some kind of an ideal Fermi gas, okay, so let's say there is some physical property. Okay, so let A be some physical property. Some physical property, and let us say that let A go like e to the power alpha uh, if um, if the gas is considered classical. Then can I say that the same property goes like t to the power alpha plus 1 if the gas obeys Fermi-Dirac statistics. Okay, so this is the question. So I am trying to say that can we generally say that if we have a classical gas, if it shows some property, I don't even know what this property is. Like two examples I gave earlier, one is specific heat and the other is magnetic susceptibility. Okay, so this is, I'm trying to draw a general behavior from observed properties. So now let me also tell you why I tend to think like this. So let's come to this question: why? Why do you think this is the case? Now, when it comes to Fermi gas is quite active even at zero temperatures because there is a lot of energy because each level can be occupied by only one particle. Now you can see that if you look at Fermi gas, let's say at 0 Kelvin, at T equal to 0 Kelvin. So you have situation like this. You have all these energy levels. They are all occupied. Okay, so you have, and then there is a Fermi energy, and all these are occupied. So up, down, like this. Okay, so these are all occupied. Okay, so now what happens is that when you increase the temperature, that is for T greater than 0 Kelvin. Now what happens in this case is that only a small fraction of total number of particles, participate in thermal excitation. Process. Thermal excitation process. Now one can think of saying that the fraction of those particles. Okay, so we can say that, for example, if you have n number of particles. Okay, so for example, classical ideal gas, if you take classical ideal gas, specific heat is given by 3 by 2 n. So you can say 3 by 2 nkb. Now it turns out that this n is the total n. Okay, so here n is the total number of particles. Okay, and classically all the particles will participate in the thermal excitation process. Whereas when you are trying to look at Fermi-Dirac statistics, there is only a small fraction of these particles that participate in thermal excitation process. That means they only take thermal energy, others don't absorb thermal energy. And this n is of the order of kB. This n is of the order of kB. So then what happens is that the CV will go like T, because this n is, because since this n goes like T, CV goes like T. Okay. In the same way, your susceptibility is like you have your n mu b square by kBt. And this is number density, which is essentially n by v. And because of this reason, this n also goes like T, this implies your chi will be going like T to the 0, because that T and this T gets cancelled. So because of this, I tend to draw this conclusion that any property which goes like T to the power alpha in a classical statistics, when the same thing is applied in the Fermi-Dirac case, it will go like T to the power alpha plus 1. Okay, so this is a purely generalization that I am thinking while I am presenting this lecture. So I would recommend you also to think and see if there are some examples which are kind of violating this generalization. Then I think we can see whether our understanding is correct. Okay, so this is about generalization that we can, because this also tells us physically that important for thermal excitation process is only those electrons or fermions that are very close to Fermi node, and those electrons that are deep-seated are not really disturbed, are not participating in the thermal excitation process, or any excitation. For example, when you apply magnetic field, the excitation is not thermal but a magnetic excitation. But they are also not really disturbed if they are deep-seated from the Fermi level. Okay, so this is something that we have. There's a possibility. So that's what I thought. Okay. So maybe I will just stop here. There are some questions. Okay. Yeah. Just 1 minute.
Hello, sir.
Yeah, so I think there was a question.
Yes, sir. So you said that when we apply the magnetic field, the particles lower their energies by converting from spin down to spin up,
Mhm.
uh, so that so they try to attain the common uh, Fermi energy.
Yeah.
So why that system would try to attain the common Fermi energy?
See, it is like if you have see, essentially the point is that the system will always um, try to minimize its energy, right?
Yes, sir.
So what happens is that if you are Fermi energy, so initially if the Fermi energy difference is there like this, now the particles which are here will find that there is some energy levels in this side available, so they will make a transition. And in the basically transition means this side it is down spin and this side it is up spin. So they go from here to here. That is possible by making a transition of their spin orientation. Physically, that means that it is like when a magnetic field is applied, a spin is orienting along the field to minimize its energy. But that will be corresponding to small lowest energy.
So basically, it is trying to minimizing the energy. It is
Correct.
like here it is. So here it is the Fermi energy ultimately.
Correct. Correct.
Okay, sir.
Okay, so if there are no questions, maybe we can stop. We have some Viva here, so I thought I should attend that Viva. So that is why I thought I will stop 15 minutes before. Okay, so can we close?
Okay, sir. Thank you, sir.